So specifically, we will discuss diagrammatic and field theoretical methods, diagrams, and later then field theory. And we will formulate this discussion.
Microphone, please.
Sorry. So we will formulate this discussion for the RMT, within the RMT setting. Now the RMT model, I mean this Gaussian distributed model Hamiltonian, in a manner of speaking, is a harmonic oscillator of disordered systems theory. So it's the simplest model system by far you can formulate, which is of reasonable conceptual generality. And we will discuss this concept within this framework here. Now you have been exposed or will be exposed to at least 3 non-harmonic oscillator applications of the same concepts, which are Anton Andreev, Alex Kamenev, Alex will discuss. You will discuss this order, right?
I don't know yet.
Okay, I mean, but certainly Sasha Milling next week, so that will be hardcore. So you may ask yourself, why operate in this silly framework here, while there is so many more interesting settings around. The point is that this here has the benefit of simplicity. So many of the concepts which are of general validity, I mean, far beyond mathematics theory, can be nicely exposed here, and that's why I'm discussing stuff here. So there are more interesting applications around. In some of them we will touch when we will advance into the discussion of non-standard symmetries somewhat later. So one kind of conceptual structure I would like to draw your attention to can be roughly anticipated as follows. So we have our disordered system, and we saw that there is some symmetric space at work, right? So we can discuss. I mean, I don't want to recapitulate that, but you remember there was a symmetric space. In fact, depending on the symmetries, 10 different symmetric spaces. 3 of them had surfaced so far. Now, when we compute disordered systems, we rarely do that except if you do numerics. I mean, but if you work analytically, normally you average over realizations and then work in some average framework. For example, in the RMT setting, we would average over our maximum entropy distribution of Hamiltonians, and then you work in some kind of effective theory. And what I want to discuss and show is that, again, there is a symmetric space around here. So much of the structure of the effective theory is governed by and these 2 guys are different. So this is one of our 10, and this is another one of the 10, and they operate in different spaces and so on. So there is some kind of duality around. There is actually a fairly highly exposed or developed duality. And understanding this is of some general usefulness, I believe. So that's something we want to discuss in how all that works, and hopefully today. So since there are altogether 4 discussions of the same thing, namely quantum field theory of disordered systems, I would like ideally to advance at a relatively steep pace, but you can always slow me down if it's not too fast, right? Okay, so first diagrams. Okay, let's just tease up anything, right? What we formulate is a diagrammatic approach to RMT Hamiltonians. And I will restrict the discussion to Hamiltonians of type A, unitary symmetry, or A1, Symplectic is rather similar. Now, once more, I mentioned it yesterday. These diagrams are not. I'm not discussing them because they are terribly useful too. In fact, they aren't. They're not useful for anything, except for they tell us a lot about the conceptual structures around in the theory, right? So it's like a pedagogical type of thing. And to be concrete, we consider. We want to consider some observables. One of them is a trace over the single particle resolvent operator or Green function, and is epsilon plus minus h. Or the second moment of this.
To the minus of.
Ah, yeah. Namely, let me write this capital here. Excuse me. Plus omega. So typical two-point function, if you want, two-Green function. And you understand that once we know these two guys and their averages, then we can compute things like the average density of states or correlation functions of the density of states. Yeah? If you want to do more fancy things, high-order moments, you have to go to higher. You have to add products of more Green functions. It gets more complicated, but conceptually not much will change. Now the Hamiltonian appearing here is now our matrix Hamiltonian, so we can think of it as some in terms of some finite dimensional matrix, n-dimensional matrix, described in terms of either complex or real matrix elements, depending on the symmetry class in which you are. And we draw these matrix elements from a Gaussian distribution. So it's a statistical theory, and the Gaussianness of the distribution can be equivalently expressed in terms of the second moments of these matrix elements, right? And these second moments are given by let's get the Gaussian theory. So like this. And that now again depends on the class in which you are. Yeah?
What is that small 18?
Here?
No, to the left.
Left is here.
Left.
There's some little.
Ah, here, that's a trace. Trace, sorry. So we compute two traces of Green functions.
So trace in the trace.
No, the product is two traces.
Two traces.
Two traces. This is a trace, and here's another trace. So we compute the trace of the Green function, either recurrent or advanced, and at some point we will average the whole package. And from that we can compute the correlation functions I discussed before. Because they were moments, second moments of, this gives you the density of states. And if you want to compute the second moment of the density of states, you. All right, so these moments now depend on the symmetry class. In the class A case, unitary, they are given. Remember, I mean, the weight function in the distribution function was e to the trace h squared, right? And if you then average two of these matrix elements with respect to that weight, you get nothing unless the matrix elements are paired like this. Prime. And then we had our Gaussian weight factor, which gives us the lambda squared over n. Lambda, to remind you, was the width of the spectrum and n the dimensions of the matrix. Is that clear? That, I mean, or should you understand this? Or you get this?
Why did you change mu and mu in the second part notation?
Because when you write trace h squared, it is yeah. They're just paired in this way. Now, in the orthogonal case, this is a symmetric matrix, so it doesn't know whether it's mu or mu, so you get a symmetric combination here. Mu prime delta prime plus mu prime delta mu prime. And again, the same lambda squared over n. Remember our discussion on this beta factor yesterday, beta 1, 2, and so on? It's made in that such that you get the same linear coefficients here. Okay, our task is now to compute averages of these moments, averages with respect to this distribution. That's our job, right? And we will do this now in attack this problem in perturbation theory in a funny kind of perturbative scheme. Namely, we will expand our Green function around the center energy in powers of 8.
First one is the asymmetry, the second one is A1.
Yeah. That is so we do a perturbation theory in H, brute force, stupid thing to do.
You're perturbing around h equals 0.
Yes. Well, there is nothing else to perturb around other than 0. I mean, we assume that E is large, and I mean,
But it isn't, right? You're interested in E in the middle of the spectrum, so E is not.
right. But
Do it anyways.
yeah, we do it anyway. Yeah, no small parameter. So the way we do it is as follows. We introduce our zeroth order Green function, the unperturbed Green function, which is we denote it in terms of little arrow, but that's actually, it's not a perfect notation because this unperturbed Green function is in fact just 1 over, or its matrix elements, I give more plus minus. So it's just sitting at the side. We can label it by. So that's our zeroth order Green function. And then we have our perturbing operator, which is H. And in our graphical code, we represent it by a little something like that. And it connects between matrix elements mu and mu. Yeah? Gets us from this is H mu mu, so it gets us from mu to mu. Scattering. So think about it like, I mean, or some useful way of thinking about it. Think of mu and mu as sides of a lattice. I mean, there is no real lattice structure here. And H mu mu warps you from one lattice side to the other. And we use this kind of symbols because then we get as close as we can to the ordinary diagrammatic representation of disordered systems. The diagrams will look similar pictorially. Is that clear? I mean, what? All right. So now we say we start with this. We want to come and the homework, or not homework, we do it here. The exercise we are setting ourselves is understand the semicircle law. That's the first exercise. Remember that yesterday I told you the density of states was a funny semicircle. We want to understand it within the diagrammatic expansion scheme. And well, I mean, we just start drawing a picture. Yeah.
What is this E plus minus?
That is E plus minus I delta, and I delta is infinitesimally positive. So we suppose we want to now trace G, and say thus, and so how would this look graphically in a perturbative expansion? So to zeroth order in H, our Green function is just sitting there, and we take a trace. So we take the mu matrix element of our Green function. So we would write down something like that, right? And here is the sign mu, and we sum over mu, and it's just 1 over E. That's what I'm telling you, n times. Now to first order, we get something like that. A single scattering, but we have to get back to the same mu, so it would be a diagonal matrix element of H. We have to sit there. And then we carry on, and we get such a little hedgehog. So, and we get these like that, and lots of dangling bonds here. And that's pretty much it. Now, we average this beast. So we might which means, now we subject our dangling bonds to this rule in a way, right? So each of these little crosses has, where we get here from mu to nu and here from mu to nu prime and so on, has to find a partner such that they get aligned in this way. Yeah? So pictorially this means that we kind of connect and identify sites in this way. Right? So if we take two of them in average, that becomes something like this, and the matrix elements are then to be identified in this way. Is that good? Yeah? Okay. So the rule of the game is draw all possible pairings of these dashed lines, and we get a total mass. I mean, say, at high orders, we would get something like this. Lots of lines. Yeah. And we stare at that. No question?
How do you get from the first one?
Nothing. H by which is 0. So you need even orders to get something. So we get a messy stuff. Yeah.
You connected up with this particular there, you assuming something about the symmetry class?
No. So far, I come to that. I mean, so far I want to let's focus on A for a moment. Just to I tell you the difference.
Alex?
Yeah.
Can you give comments? I mean, so this diagrammatic looks very similar to if you were working with just a disordered.
Of course.
Yeah. And then just average over random potential.
It's absolutely the same.
Here, there's no space.
There is no space here.
So is there some limit of?
Yes, it's in a way we describe something which is physically equivalent to the zero-dimensional limit of diagrammatic perturbation theory. But
so for these quantities, am I supposed to give the same answer, or I'm supposed to take some limit of the
if you do a diagrammatic expansion, like Russian-style diagrams, and you go to the zero-mode approximation, so the diffusion operator is you go to the gap regime and get precisely the same answers.
But you don't have a small parameter here.
No. Yes, indeed.
So that's, I think, important.
It will not. I tell you about what my parameters are.
It's a Gaussian.
Huh?
It's a Gaussian, so you can get away with it, right?
But I promise I will be within the radii of convergence of this theory. There will be problems popping up, but not yet at this level. All right, so we have this. Now there's nothing we can do with such a messy thing. But now we invoke an expansion parameter which we have, and there is indeed one. Namely, what we aim to do is we want to send n to infinity, keeping lambda fixed, right? Keeping lambda fixed. And what does it mean? Look at this beast here. So whenever we add another cross pair, we catch a factor lambda squared over n. And in order to survive the n to infinity limit, this 1 over n has to be compensated for by a free running summation over indices. If it is not, then we catch a factor 1 over n and it will kill us. Conceptually, it's the same as neglecting cross diagrams in purity diagrams. Huh? Same thing. So that means that, say, something like that is perfectly okay because you have nice freely running summations here. So that will be okay, but if you look at this structure here, then you get too many Kronecker deltas of indices, and you have to pay dearly for that, namely there's a factor 1 over n compared to this diagram. Is that clear, the idea of this argument? So the essence is that in the n to infinity limit, we can neglect all diagrams where these dashed lines cross. And we retain only the non-crossing diagrams. It goes by different names. In surfaces and various different concepts. Non-crossing approximation, self-consistent Born approximation. It's all the same thing. So let's now, within the framework of this approximation, or given this approximation, we can compute this. Yeah. And let me write it like such. The average Green function, even before taking the trace, and I'm omitting energy arguments and so on to keep the notation slim. Let's denote it by a fat arrow. And it is given by the zeroth order Green function plus so it's a self-consistent equation which sums over all non-crossing diagrams. Is that clear, or should I comment on that? I mean, what this is here is these are diagrams like this one plus this one plus this one. So they are all, if you self-consistently expand this in increasing number of dash times, you get precisely this series. I see. I mean, is that clear, or ask if it's not clear?
So that's controlled by log n or not?
Yeah, that's exactly the everything which is not captured by this line here, by this beta equation, is of lower order in 1 over n. This is summing over all diagrams with non-crossing utility lines. Okay. Yeah.
How do you distinguish between G plus and minus in your features?
It sits here in 1 over, I mean this here is 1 over e plus minus.
The direction of error, or the direction of error?
No, it's not in the direction of the you will see it in a moment, this e plus minus, when we actually solve this equation. I mean that's just a formal equation which we, and now we translate to a formulas.
You started at one dotted line right at the beginning of the double arrow, and then you came
Oh yes,
down in the
it's,
middle,
yeah, sure.
which looks significant, but is
Yeah.
that really what you meant? No. Okay.
So,
So it's a single arrow before.
yeah, single arrow before, yes. And then, exactly, sorry. So this equation, depending on the concept, but goes often by the name beta equation or self-consistent Born approximation. Self-consistent Born approximation. So we can solve this for the fat arrow. Everything factorizes here, and we write our fat arrow equals 1 over inverse of the light arrow minus some kind of self-energy. And the self-energy is given by this piece. The same equation again. And what this here indeed is, it is lambda squared, and then again the trace over the Green function again. This, the full Green function. And this is the full Green function sitting here. What we are doing here is because these indices are the same, mu, we are tracing over the Green function. And then we have here lambda squared over n from the impurity line. So, and here's again the Green function. So we have now an algebraic equation for our Green function. So if we trace over this, or what we obtain is that we can put it like this: g plus minus equals e plus minus lambda squared minus 1. And what I'm investing here is that the Green function itself, I mean, it's a matrix, and here we take the one thing. We have to sum over the mu matrix elements, but nothing depends on mu. I mean, we have averaged everything out, so the trace compensates for the 1 over n. Yeah. So that is, is G plus minus is shorthand notation for this equation. All right. Now, if you equivalently using this identifications, self-energy equals that, we can translate this here to an equation for the self-energy, because this here is essentially self-energy divided by lambda squared. And then we get something like sigma plus minus equals E plus minus. Equals lambda squared E plus minus sigma plus minus. So we obtain a quadratic equation for the self-energy. A quadratic equation sounds like a circle already. No? So, we can solve that and write sigma plus minus equals E over 2 minus plus I lambda squared minus E over 2 to the power 1/2, provided modulus E is smaller than 2 lambda. So if our energy is in the band, remember yesterday we had this this notion of the semicircle, and if our energy is modulus is smaller than 2 lambda, then the solution of this quadratic equation is given by this here, with this square root sitting around, and notice this minus plus here. That's important, because the sign of this imaginary part is dictated by the infinitesimal sign of the, or offset of the energy. So depending on whether we are advanced or retarded, we get different imaginary parts. You have seen that in other contexts before, right? So that's what we get. And if we plug this now into our Green function, again, where is it? Like here, for example, and take the trace, and we get indeed the Wigner semicircle. Right? You see it here. Okay? So, rho of E.
These are all disorder average.
Huh? What?
Are these disorder average, like the equation G plus minus, that's all disorder average? No.
Yeah, they are all now averaged over.
Disorder average. What have over
Yeah.
averaged over the.
Over realizations of it. Yeah, over the distribution of it.
How do you get this G plus or minus? Is it identical? Yes, this one. No,
Here
the
for
other one.
either
This, no, the other. Yes, this one.
That's just so this was by definition G plus minus. So here you have this, and then you have sigma, and sigma is again G plus minus.
So I am looking at your picture. You have an arrow in the picture. No, just yes, that picture. No, this one. Yes.
Yeah.
So this first arrow,
Yeah.
denominator,
Yeah.
is Green's function, which is 1 over E. So 1
Yes.
over. Oh, okay. So
This is 1 over E over E. Is
okay.
Okay. So that's, brief exposition of an example how such a calculation is done. Now, what do we learn from here? So, except for we reproduced our semicircle. So what can we kind of take home from this? One is a phenomenon that there is something going on which is weakly at this point, but will become much more will become substantiated later, which reminds one of spontaneous symmetry breaking. In the following sense, in our original, the Green function, where do we have it? Here. Here you have, in the inverse of the Green function, you have a seemingly small distinction between retardant and advanced, just infinitesimal offset, right? But if you look at the average Green functions, this gets blown up to a massive distinction. There is a solid self-energy, and it has an imaginary part, and its sign is determined by precisely this infinitesimal parameter. So it looks like some symmetry is broken in some way sense, yeah? And so this gives us a hint in which direction to look. And so there is a hint at symmetry breaking. second message we take from here is that our average green function in the end of the day is side diagonal. I mean, the green function never gets away from its side, right? If you average, so that's in a kind of, semi-classically speaking, there are no, if you average the green function, there will be no, you couldn't draw extended path in this lattice space which would survive impurity scattering. Which means the physics behind it is as follows. If you consider the diagrammatic expansion between non-identical sites, yeah. I mean, in this here we take the trace, but suppose you take something like that. I mean, the heuristics behind it is it's like an extended path for our lattice, and it picks up some action. I mean, and this action is random. It's due to these many scattering phases we pick up along the way. And if we then average, you average essentially over a random, complicated random number, and that gives you zero unless the path is zero length. Okay, so that's the picture behind this short answer. So now, given this kind of input, let's now look in the same language at products, and then it gets more interesting. So we do now the same and look at trace E plus, say E plus omega over 2, trace G minus of E, and all that averaged. So what we should do now is we have two green functions, and for each of them, for each of these traces, we play this game over there. So we draw, before we average, we draw something like that. This is our first green function, and it has all these dangling bonds actually. That was a typical path contributing to G plus. And then we have G minus. So we draw a similar structure, sitting maybe here, and again, lots of dangling bonds. These like sums, right? Okay. Now we average. So what will happen? These courses now all have to make up their mind what they want to do. Right? One option is they mate with their colleagues from the same green function. That will then contribute, it will, I mean, effectively renormalize the outer green function, or contribute to the renormalization of this effectively thin line to a fat line. And then we can forget about it. That's, we take this into account by mentally replacing the outer line by the double line. And then we have taken into account all self-matings of the crosses. But some of the crosses may actually decide to pair with the other green function upon resolution. Yeah? I mean, everybody has to make up its mind. And then, in principle, you get again a mess. I mean, a highly entangled network of crossing lines in here. But what now again, what strikes or what applies is our 1/n selection rule. So if you have something like this or that will, for this you have to pay in terms of powers of 1/n. You do not get for every line a freely running summation. So that is bad here. The guys that survive are nicely regularly ordered data structures. So here you can see for every side you get a free summation. As in an RPA approximation. So what I'm trying to tell you is that this beast average in the to first approximation becomes this thing. Okay. Yeah.
So concerning the diagram that you just traced with the maximally crossed lines, so if you have time reverse symmetry, can you also in this zero-dimensional case untwist this maximally
Yes.
crossed?
Yeah, I'm coming to that.
Okay.
Exactly. That is one diagram we get, and it's exactly your point. We get that in class A, also for A1. Yeah, but in the symmetry class A1, we have another option. Namely, we can, in a way, at each of these, we can reverse the arrow, which means that we effectively, instead of H, we have H transpose sitting there. Right? We just reverse all the indices. And since the orthogonal class doesn't distinguish between H and H transpose, we get another diagram of the same type, but with reverse arrow direction. In the class A1. So that is our first distinction between the symmetry classes. Yeah.
So can you clarify what the meaning of direction of arrow is?
Yes, if you, let's see, I mean, when you have this here, and you go across, you have here H mu nu, and so you would have here H mu nu. But if you now reverse the arrow, you also, I mean, by definition, you reverse all of these indices here. Yeah, here you get from mu to mu, and here from mu to mu. And if you reverse the arrow direction, you flip the order of the indices, and the orthogonal class is blind to that operation.
Does it correspond to time reversal symmetry
Yes.
operation?
Right, exactly. The arrows, I mean, the very good point. The arrows, I mean, so this is a past reversed in one time direction, and this is of course in the counter-propagating direction. And here you reverse, in a way, the sequence in which the past is traversed. And reversing the sequence is not of any consequence in the class A1, but it gives you the complex conjugate of a scattering phase in the other class, so class A doesn't cover it. But that's an a posteriori interpretation of what we see here in the stupid matrix.
So in your 1 over n
Yeah.
jargon,
Yes.
why don't you have a 1 over n punishment in the second diagram? Because it's maximally crossed in a certain time frame.
Well, no, you can represent it as maximally cost it, but then you reverse again the direction of the arrow. Right?
So this diagram is
Yes.
identical with the first diagram you have drawn, and you said that
No,
was-
it's not identical. Why do you say it's identical?
I mean, because I remember you had different arrow directions
Yes.
in that diagram. I can take one of the circles
Yes.
and apply time reversal operation. I'll get exactly this diagram. In A1 class, of course.
Yeah, in the A1 class, the maximally crossed, exactly, the maximum, in the A1 class, the maximally crossed is identical to the totally uncrossed, only like that. Indeed, these diagrams, historically, they are known as Altschuler-Schlossy diagrams. And if you look at 1986, for this ordered system, and if you look into their paper, they represented them in a different way. I mean, it's diagrams, you can always redraw them in different ways. And indeed, it was one diagram inside and a maximally crossed on the other. This is the unfolded.
Yeah, I actually don't have a problem with these diagrams. I didn't understand what this 1 over n punishment rule is.
For the maximally crossed in the orthogonal class, you don't pay your 1 over n.
Okay.
Because you're still consistent with the ordering. I mean, there's still enough order in the diagram.
Okay.
But personally, I prefer never to draw maximally crossed. I find it terribly confusing. I always draw diagrams with counter-propagating or identically oriented arrows.
Okay.
And we will see how this is useful when we talk about superconductors.
I mean, but this is a way to see that it's not suppressed by 1 over n, because maximally crossed can be written as non-crossed but error reversed.
Yes.
And then you just
Yeah.
multiply matrices in a different order,
Indeed.
and so it's not
Yeah.
suppressed. You still are creating it.
But maximally crossed does not exist in A1. In A. Okay.
So sorry.
Yeah.
I guess you already alluded to it. So in principle, these arrows in your diagrams, I mean,
Yeah.
the Green's functions, they are double functions, right?
What?
Do they already SCBA Green's functions? These-
They are fat, yeah. These are all fat lines. I just don't want.
Yeah.
Good. So if you look now at this piece, and you you see that there is kind of 2 letters around, right? There is on each ring we have such dot which you can really place somewhere, and then they're connected by two letters. So we need to compute these letters. So what we have to compute is a building block or compound block in these diagrams, where we start with mu and mu. And you should think of this as an entire geometric series result, right? And you can do that, and I will spare you this calculation in exactly the same manner. I mean, you run the same type of computation, and what you find is that this is given by I times lambda squared over pi times 1 over s. And s, to remind you, is s is what? S is pi omega over delta. So they blow up they become singular in the low s limit. If you physically, what's behind that is what you're monitoring here is a path of a particle, and here, I mean, here's a retarded amplitude, here's the advanced amplitude, but there is a slight mismatch in their energies. So the kind of scattering phases you pick here, up here, and here almost compensate, except for this difference, and we are in 0 dimensions. So if you sum over all these contributions and you send that difference to 0, you have so much phase space. I mean, so much to sum that you get a singularity. Yeah. I mean, if S is large, you have only a relatively short path to sum over, because you will be coherent because of this kind of phase difference due to this energy difference. But for small s, you can sum actually rather large paths, you get a lot of summation volume in 1 over s. It's a wishy-washy argument, just trying to motivate that there's a singularity here. Is it cryptic what I said?
Are there some factors of n around? Because you're going to sum over mu n nu and
No, I think they are all.
you're going to get
I think they are more or less okay. So that's one thing. So there is this kind of significant. Now, if you look at this here, what this is actually is a transition probability, not amplitude, but probability to go from mu to side mu in your random environment on average, right? So how do you compute probabilities in quantum mechanics? You take an amplitude, here it is. You square it, here's the other one, and that's what it is, right? So, and that is here kind of a classical approximation to a transition probability, because you go here along the same path. I mean, this is one path, transit path, this is another one, exactly the same scattering sequence. So that we should think of this as some kind of classical transition probability, conceptually. And let's call it this piece here, P mu mu. It doesn't depend on mu nu. It's totally, that's our random matrix Hamiltonian. I mean, there's no structure, it's just a constant, like such. Okay, so what we learned from this calculation, if we plug it in, is that our 2-point correlation function is essentially 1 over s squared. We have 2 of these guys. Yeah. Remember yesterday we had this sine function, sine square s over s squared. So at this level of approximation, we conclude that what? So lowest order diagrammatic relations here gives us the answer that R2 of S is given by all the correct prefactors, I mean, and 1 over s squared in class A, and 2 over s squared in class A1, because we have two diagrams. Yeah?
Why can't I just bring the vertex right next to the other vertex and then draw one line through it and say it's just one propagator? So if I take the internal circle, turn it around,
Yes.
so that the centers, basically draw a straight line to the centers, shouldn't that give you one diffusion, one double?
Only one line, one letter?
Right.
No, never. That you will not find. Because no, that is not a valid operation because you couldn't do that without crossing. You have to take a scissor to do it. Because you first have to cut all these guys, then turn, and then reconnect. But you must never use a scissor while working with diagrams. Pair of scissors. Answer? Yeah. No, you would really miss essential summation volume with all the phase space in it. Yeah?
Do you have to trace over P mu mu plus mu
Yes,
and mu?
we are taking here P mu, and then we sum for mu and mu. From where we see that in appropriate units, David is right and there's a factor of 1 over n. Yeah.
So in this summation of these ladders, so I guess one of the lines will be something like E plus S, right? And the other one like E minus S, roughly.
Here? Yes.
Right, so
Indeed.
it's somewhat independent of E. Right?
No, it's E plus minus sigma, right? Yes.
Right.
And
The result does not depend on E.
they do, they depend on the. Can we discuss in private first?
Okay.
But I promise they do.
Okay.
Essentially, yeah. I mean, I can do the calculation here, but
Okay. No, I just wanted
Yeah.
to understand the
yeah. No. So we get a promising result, the first order, but it's not the full package. I mean, there was more. And now one more remark concerning the conceptual status of this P, and having, I mean, kind of Leo's earlier remark in mind that this looks all like the diagrams in disordered systems. So you get analogs of these structures for disordered or chaotic systems. I mean, just saying what changes essentially is the interpretation and nature of this P. But a P is there, and to get a somewhat better understanding what this P is all about. So I already argued that this is a classical probability to go from mu to mu, right? Now, and it is 1 over s in our case. If you Fourier transform to time space, you would find that P mu nu of t equals theta function of t. So in the random matrix environment, it is so structureless that the probability go from mu to nu is positive and constant, provided you have positive time. Now let's just, I mean, kind of anticipate what in a real disordered matter, what would be the analog if we would do these calculations with real impurities and string function. What would change is
this is
huh?
large S. Right, this is an approximation is valid at a large S, right?
yes,
So,
it's
so we're talking about that's the short time structure.
that is a compound building block in our diagrams, and if you go to short s, you just don't get away with. I'm coming to that. But
Yeah.
At this level of approximation, I mean, this will always stay what it is.
That'll stay a state of T?
That in random matrix theory, but there will be more P's popping up. I come to that. I mean, there's, yes?
I guess there's a 1 over n there.
Yeah, it's proportional to. Yeah.
Stupid question. How can you interpret this as a probability if it's imaginary?
It's proportional to the probability. In fact, you can because we're working in energy space here, so it's a Fourier transform of probability that I can sink in. Now let's just to give you an idea of where this would go if we would work with actual disordered metal. Just to draw some analogies, P would then be replaced by the classical probability to go between two different points in space in your disordered metal. So it would now be the classical probability to go from x to x prime, and in a diffusive environment, the Fourier transform of that would be the diffusion pole. I mean, classical probability is governed by kind of Fourier transform of the diffusion, and then you could from there compute x of t, and that would be the diffusive. I mean, would be the diffusive probability to propagate from x to x prime in time t, and you all know how it looks, right? So diffusion propagator. And that is exactly this Perron-Frobenius operator I've been talking earlier about. Remember, in the very beginning, we said there is a classical, in a disordered system, there's a classical propagator around, which is effectively irreversible, and it tells you what's going on in the intermediate regime. It's precisely this. This is the effective irreversible propagator that tells on the classical level what the dynamics in your system does. In a disordered system, I mean, if you have a real disordered system, these Qs here are quantized. They are momentum modes in a finite size system. And the lowest non-vanishing Q goes like 1 over L, or pi over L, or 2 pi over L, depending on boundary conditions. Right? So there's the lowest non-vanishing eigenvalue. And, so lowest non-vanishing value of this guy here scales like d over L squared, which is the inverse of the time you would need to diffuse through your system. If you go to much larger times, means much smaller omega, this is a massive term, the non-vanishing. And then to a good approximation, you can restrict yourself to the lowest eigenmode, which is the zero mode at smaller times. And on this level, in the zero mode approximation or at very long time scales, this becomes 1 over omega, it becomes precisely our random matrix. So that is, in this limit, the physics of a disordered metal collapses to the random matrix regime. Okay? It's very sketchy what I'm telling you, just the idea. So at very long time scales, no matter what the dimensionality is, if there is no NS localization around, a disordered metal can be modeled in terms of random matrix. That's what this is hinting at. Yeah?
You said something about reversibility. I couldn't catch that. Can you?
The diffusion operator is irreversible. I mean, it's not. If you have a chaotic system, right? I mean, now we're getting to the philosophy level, which I wanted to avoid. But suppose you have a chaotic system. I mean, some fixed hard scatterers in a system, and you ask yourself, this is very large, right? What is the probability to go from here to here? And of course you can say, it's perfectly unitary dynamics, so it's what must be time reversal invariant. And so to go from here to here. But in fact it's not. I mean, and mathematicians can tell a lot more about that. The effective dynamics in a non-neutral environment is irreversible and diffusive, in fact.
Is it related to this time versus symmetry breaking you were talking about in this somewhere?
No.
Because
it's
you
just
somehow don't have time versus.
It's the same time reversal irreversibility like when you take this drop of ink in water, right? You put it in there, in principle it should be time reversal invariant, but you do not get it. It relates to entropy and what it is. It's discussion I'd rather. Let's talk about it. You see how I'm getting a little bit more agitated because I'm running out of time. As usual, I was panicked, but anyway. I stick to the statement that we can stop any time, but there is a cutoff time which I have in mind, which I'm not telling you, but okay, good. So now, that's what we get here at this level. So, question, is diagrammatic perturbation theory really restricted to this result? I mean, the real correlation function is more complicated. There were these signs around, and here a lot of other junk. Question is, can diagrams tell us more about what's going on here or not? And at first sight, it looks like not really, because it seems like I've exhausted all the things I can do, right? But what I'm telling you is that there are in fact diagrams which do not suffer 1/n suppression and are not accounted for here. And that's the key to making progress and to advance this result to higher orders in the perturbative expansion. And the nature of these diagrams is best exposed or best revealed in a non-technical language, in heuristic kind of way of arguing. So what we have been using so far is the following. You have a path in your scattering phase space. And this path, beginning and ending at some point, can in a way constructively interfere with the complex conjugate, I mean the advanced partner. So this is a perfectly phase coherent pair, and we have been summing over these conclusions. But now let's look at the following contribution. This is essentially a classical object. I mean everything is. But now let's look at the following. Suppose one of the guys does this, and there's a very shallow self-intersection. Of course, I shouldn't use the word shallow because I'm doing mathematics theory, but think about it, cavity also. Everything is really universal. So we have, and now comes the other guy. The other guy decides to spawn arrows. So the other guy starts out here, and it's really compliant. It follows its partner. But here it changes its mind. Here it doesn't go this way, but it decides to go this way. And this is a very soft intersection. There will be, this will be a rather coherent. You can make it as coherent as you want, right? By going, so it goes this way. And if everything is done here rather softly and nicely, this will be a phase coherent pair. If A1. Because look at the relative orientation of the arrows, which I forgot. Here I start this, and here I'm now propagating in the same direction. Yeah. So there will be some price to pay here. I mean, because here there's some disruption. But the hope is that we can sort of compromise and make this reasonably cost efficient. And
in random matrix theory, there's all intersections are shallow. You just go
yes,
point.
exactly.
Okay, there's no.
Precisely. So in random matrix theory,
so that's really the shallowness is only a statement.
Exactly.
More broad.
Yes. But in random matrix theory, what we can do precisely is we can draw a diagram. Like this. And here. And here we put now our letters. Here is some intersection region about which we have to think a little bit. So there is some stuff we have to add here, and I don't want to go too technical, but believe me, you can add here a few renormalizing impurity lines such that you are still in 1/n okay, and you get this as a diagram which survives the into infinity. In the jargon of the field, in chaotic systems, this is known as a Sieber-Richter pair, for all those who have heard the names. And in the jargon of disordered systems, this intermediate region is known as the Kami box. It's only buzzwords. But you can compute this diagram, and what you find is that you get a contribution of 1/s cubed, but only in class A1. In class A it doesn't exist because you violate the rules of the game in one wing. Okay? So there is, yeah?
Maybe very, very stupid question.
No, there is no
So that's not a correction to your G plus, G minus, right? Is that
Exactly.
coming back to G, 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 not
G plus, G minus, yes. I mean, there is G plus, and here is G, beginner ring, here is G minus. So that is G plus. The path contributing G plus is 1 to G minus. What? Oh, I didn't. No?
Okay, finishing
So what we conclude from here, from this picture, is that there is in class A1, if we take these diagrams into account, we get something like minus 2 over s squared plus constant over s cubed. And on this level of perturbation theory, we do not get anything in class A. Now, remember the structure of the exact results. So that we had in A1, in A, we had 1 minus sine square s over s squared, and in class A1.
That's a different quantity.
Huh?
Because that large S goes to 1, whereas this goes to 0. This is a different quantity
Yeah, the one is always removed in our.
over here.
Yeah. We're talking about this here, and the sine squared is actually massively non-perturbative. So we are doing large S in a way, and like I said yesterday, the sine squared, think of it as 1/2 essentially. And then we, in this level, at this level of approximation, for class A, we get 1 over S squared, and that's it. For class A1, we get 1 minus 3.
Can you physically explain why this one can just be removed at large S? Is that a diagram you forgot?
No, you get it if you get it from the shortest path, which are not accounted for in the ladder. So there are some zero length paths which contribute to the game. Which I have, yeah. So it's a trivial. This one is in a way trivial. The sine squared is very non-trivial. Yeah.
Can you please again repeat? So these results are valid for S tending to 0.
For large S, S much larger than 1.
Oh, that's for S larger than.
Yes, it's much larger than 1. For S smaller than 1 and smaller, we run into non-durable problems here with this stuff.
But for large S, this is going to be oscillatory divided by S squared, right?
Yeah, but it's oscillatory on average for large S. If you allow yourself a bit of averaging, it's 1.
Okay.
So we are blind on scales as order 1.
Okay.
So here we had here we got a whole series plus prime over S cubed plus and so on. So here there are lots of contributions. But only in class A1, and we see a hint to this here. And what you maybe believe me now at this point is that you can push this game, you can continue this game if you are really determined enough to do it, to arbitrarily high orders in these kind of snakes. Yeah? So if we look at this in high order perturbation theory, then we get structures. We get structures like such. So at high order, at these high orders, it is inconvenient to always write these kind of compound letters. So let's abbreviate them by like such a little worm here. And then we would obtain something like that. R2 of omega in class A is just this. And there's nothing more coming in the level of perturbation theory. In class A1, things are more interesting. Then we have this here, and then we saw there was this structure. That is our Sieber-Richter pair. and that is 1 over s squared, that is 1 over s cubed. And then we have something like that. Again, with here some 2 avoided and crossing pairs, or 2 Sieber-Richter pairs. But we can also have structures like such. And both are, here these are 1 over S4 and 1 over S4. So we get a whole series. Yeah? And believe it or not, people some few years ago have been crazy enough to sum it up to infinite one. In some asymptotic resummation program. And this can be done, I mean, in principle, it's, because these wavy lines here, they're essentially trivial, they're 1 over s, so there is no spatial structure around. So the structure of these diagrams sits entirely in combinatorics and their topology. If you work really hard, you can sum up the entire series.
But it doesn't converge to the exact answer.
No, it does not. The sign is always elusive. But I'm telling you how to get the sign. Good. Now, what do we learn from here? Just looking at this. I mean, forget everything, or much of what we have had to do to arrive here. Just look at this. First of all, I mean, we notice that the structure of these diagrams really sits here in, is only determined by the topology and combinatorics. There are no momentum summations and other scary things you have to do. Then I want to suggest to you the following interpretation. I mean, if you look at it from, I mean, kind of emergent perspective, then this wavy line here looks like some kind of effective quasi-particle propagator. Right? It's like some effective 2-particle propagator in the theory. So we have some kind of funny quasi-particle, discovered kind of quasi-particle, subject to weird interactions. This kind of, I mean, it's really this heavy quotes. I mean, this quasi-particle has a propagator that is singular. For long times, it explodes. And it is subject to massively nonlinear interactions. I mean, if it's, suppose it was a boson, right? And then this would be nice, it would be 2-particle interaction. But here we have 3-particle interactions, in fact, arbitrary high-order interactions, if you go to high order. So we have high-order interaction matrices. And another thing is, I mean, it's what this 1 over s hints at, suggests is the following. Remember, I threw this buzzword spontaneous symmetry breaking at some earlier point, right? We said the self-energy we discovered broke this plus and minus I-delta infinitesimal symmetry. Here, there is in fact an explicit symmetry breaking in the theory, namely plus omega over 2 minus omega over 2, which we built into our gain functions. What we have here is some kind of mode which becomes singular in the limit where we tune this explicit symmetry breaking to 0. Now I'm asking you, what does it remind you of? I mean, we have a structure with kind of modes which become singular in the limit where you send a symmetry breaking parameter to 0, and they are strongly nonlinear interactions around. Have you ever seen something like that before?
Goldstone mode.
Yeah, Goldstone mode is correct. Yeah, I mean, this should be Goldstone modes of some symmetry breaking, namely this one. Goldstone mode is good, but what does this? I mean, it could be a Goldstone mode of both a gas. Then you would probably not get this very entangled system of interactions. So, any other systems where you've seen something like that? Goldstone modes, massively entangled.
Single Sigma model.
Sigma model is the keyword. Magnets, gauge theories, like strongly interacting gauge bosons. in QCD or in magnets, interacting magnets. So this is a hallmark of such theories, and all of them have in common that they are described in terms of nonlinear sigma model. Nonlinear sigma model being here to be understood as a field theory subject to a nonlinear constraint. Yeah, so what this hints at is that there is some kind of quantum field theory around which describes the low energy physics of the system, and this quantum field theory should be a nonlinear sigma model. That's something you knew because there's lots of lectures on nonlinear sigma models here in this program. We're just discovering it a kind of a bottom-up approach, that there should be something like that. Yeah?
You're claiming this describes the low energy physics of the model, but this is only a convergent series in the high energy limit.
Yes, exactly. So we are asking here, we discovered here the perturbative expansion of an would-be low energy quantum field theory which sits in the cellar at low energies and just waits to be discovered. Yeah? That's, we're approaching the problem perturbatively, coming from high energies. Okay, so that is as much as now you may ask yourself why doing all these diagrams and torturing you with this. You knew already there are field theories of disordered systems, and one thing I'm doing this is because later when we discuss non-standard symmetry classes, such type of pictures are very good at discovering structures which otherwise easily go missed. Yeah? So we will get back here when we talk about the non-standard guys. On chiral symmetries of superconductors. What's the question? Yeah?
So the retardant and advanced Green functions are two ways of breaking the symmetry spontaneously.
Yeah.
But presumably they're part of a continuous manifold. But does the rest of the continuous manifold have any different interpretation as like meaningful Green functions?
I think I just didn't get it.
So you said that the retardant and advanced Green functions, so plus I epsilon becoming a plus I something finite.
Yes, exactly. Yes, yes.
So those are two ways of breaking the symmetry spontaneously.
Yes.
But I mean, that's a discrete set, and this is a continuous symmetry that's being broken here. So
yes, we indeed no. I mean, we discussed precisely this point. I mean, it's as in a magnet. Yeah.
Okay.
You have an infinitesimal magnetic field, and then. I mean, we will get there. It's precisely this. So yeah. So let's now try to identify the kind of low energy theory that generates these structures in a perturbative framework from a different perspective than by just constructing the field theory. Yeah, and before doing that, I would like to draw your attention to kind of tune your attention in a particular direction. Follows. So that's now remember in the beginning I mentioned some kind of duality of geometries and so on, and we can see a first hint to this effect already at this level, entirely based on the diagrammatic framework. And we can do that by following way. So our basic compounds in which we used to formulate our diagrammatic expansion were retarded and advanced string functions, right? And here we have been working in a setting where we had one retarded and one advanced, but suppose you want to calculate a high order correlation function, then there could be 5 retardeds and 4 advanced or whatever. We could have more of these string functions. And let's label this by giving them a counting label, A, which runs to 1, 2, 3, and so on, which counts in order, and a little plus, which chances that these are retarded. And here we have correspondingly an index A minus, and these are the advanced string functions. And this A plus goes from 1 to n plus, and A minus goes from 1 And then plus and then minus are some integer numbers. Yeah. And now we could start again constructing our directives. And if you think of these here as kind of quantum amplitudes propagating, or some fields propagating, then these fields would be would naturally carry two labels, namely psi would carry label mu for our Hilbert space, right? It lives in some Hilbert space. But we would also have to add this bookkeeping index A. And A is now either A plus or A minus. So these are the, in the natural way, it's indexing our degrees of freedom. So our degrees of freedom, in a way, they live in the Hilbert space, which we call HC tensor HF, and this here accounts for the new indices, and that these are the A indices. And I want to call this here the color space, and that is a flavor space. So the colors we run from 1 to n is our big random matrix, and there's a small, relatively small order one-dimensional Hilbert space L which just contains just bookkeeping about our indices. And we will see, I mean, color flavor I'm using here just because I don't want always just marker if you want. But we will see later that this is actually, the notation isn't that bad, because these are precise. And we talk about this color and flavors in QCD in some state. Yeah?
Are you allowing n plus and n minus to be different?
They could be, but think of them as, yeah, they can. But,
If they're different, then what do I think of as the Hilbert space?
Oh?
If they're different.
No, then we have an n plus n minus dimensional Hilbert space. I mean, the dimension of HF is n plus n minus. Okay? So, now this is the basic arena in which we operate. And now let's look at the quintessential compound of our diagrammatic experiment, which had this fraction here. Yeah? So here we have our random matrix indices, and they have to be identical. Mu, sigma, so on. To be identified indices in the random matrix space. And here we have our.
Those say pairs of indices.
Yeah, I mean, if this is here, if this is h mu, this is h. So this is the here entering inside mu, and here we get inside mu. And here we have our A plus index, which of course stays A plus. Yeah. Nothing happens here. So this is one and the same amplitude, just walking through this random environment. And here's another one, which is an A minus. Yeah. Okay. I mean, no big deal. That's how it looks. Now look at the situation before average. So then we have, look at the single one of these guys. And what's happening? There's a lot of going on in color space. We go scatter from mu to mu and then on and on and on. And nothing happens to our flavor index. The flavor index is dead before averaging. Same down here. So they are just like bookkeeping index, totally passive. After the averaging, we should focus in this direction. So now we have always these color indices are always paired up to some color singlets. I mean, the theory in color space after averaging doesn't transform anymore in any non-trivial representation. It's just dead. We averaged out everything. But all of a sudden we have two different flavor indices correlated. And interesting things can happen because these here can actually turn in a different way and then pair with some other flavors to combine to something totally different. So before averaging, the theory is alive and kicking in color space and dead in flavor space. And after averaging, it's dead in color space and alive in flavor space. No? Yeah?
So why are there no lines before averaging in flavor space? Why are there no impurity lines in flavor space before averaging?
The notion doesn't even exist. I mean, the impurity lines are a concept in, I mean, it's our Hamiltonian, our big Hamiltonian, H mu, which is a color space object. All I want to say is that
So what do you mean that it's alive and picking in the flavor space? How can you change the flavor?
you can because you can draw, for example, diagrams like that. So here is one green function doing something, and here comes this third green function. No, that's I need more than 2 green functions then, right, to do something. And right? And what's happening here? We have A plus A minus B. And I screwed it up again. No, yeah. Sorry. Yeah, this is sorry. This one. B minus, B plus. So now after averaging, you can correlate between A plus A minus to an A plus B minus mode.
Okay, so it's labeled by a pair. So you cannot check anything on the line, you can change just the pair.
Yes. I mean, there is, right.
So your worms carry 2 flavor indices.
Yes, the worms carry 2 flavor indices.
And one is advanced and one is returned.
Exactly.
Except in Model A.
Yes. But even in Model A, if you don't look at the 2-particle green function like that, but like conductance or so, transport coefficients, then you also get your worms in A.
Is this like 2 worms coming in?
Yes.
And they somehow scatter?
Yes, exactly. And they go on. This is precisely in our abbreviated notation, this would be something like that. Where here you have an A plus AA, and here it becomes AB. Another, I'm throwing buzzwords here. It's like planar matrix theory. So it's yeah.
Does it have to stay planar? Well, if it doesn't stay planar, you lose a factor of n.
No, you can. I think you can represent it.
But usually things are planar because if you have them non-planar, they get suppressed by a factor of n.
The factors of n are already away.
Okay, well maybe we should just take your word for it that they're planar.
Forget this planar. It's planar. Okay. All right. So what we anticipate is, but we have to show it, of course, how it works. But the anticipation is that we have. We have what? We have something like a flavor space, namely this one here, which we can identify as C to the n plus n minus AF. Then we have a color space, which is C to the n, that is HC. Our psi's live in the tensor product of these 2 spaces. And we know that quantum mechanical time evolution was described by a symmetric space acting in HC. Yeah? So we have, it's represented in terms of tensor matrices like U, where this U was taken out of our M manifold. And totally passive. This doesn't do anything. Now, that is, and there was a color symmetric space there, which was the governor of this dynamics and which controls what's going on. In the average low, if we average the theory and go to low energies, we have 1 in color space because everything is averaged out. Averaging is controlled. And here, we expect to see the player U tilde, which we expect to be unitary. I mean, reasonable theory should be unitary. And the question is, what is this? I mean, what is this? East, and what we will discover is that this is again a symmetric space. I mean, there is a second flavor symmetric space sitting here, and they are partners. Depending on the symmetry, you can always identify one here, and there is a partner here, and they are different. They act on different degrees of freedom. They are symmetric spaces nonetheless. And understanding these, there is not much you can do with these symmetric spaces in really analytically. On the computer, yes, but in practice, you cannot really work with them. They are too complicated, too high dimensional. You can maybe identify a topological index, but not much more. But these guys here will be very user-friendly. With those, you can do quite a lot. I mean, it works. Sometimes it fits your Okay.
Okay, can you just repeat again?
Huh? As many dimensions as you want to have green functions on board. These two.
But they're user-friendly when they're low-dimensional, or always?
A user-friendly is a really a relative term. But they are better, I mean, it's better than a 1,000-dimensional. I mean, yeah.
So one question is probably maybe also going to say it next time, then just to be quick. What about the compactness and non-compactness? So depending on this, if the pairs are pairs of bosons or fermions.
Oh yeah, that's a very good question, right? I mean, if these are fermions, they are compact symmetric spaces. You can develop the theory also for bosonic, even if these are in principle single particle green functions. But you can represent them, and we will see how in terms of either fermionic or bosonic fields. And if you work bosonic, then you obtain here, then you go to non-compact symmetric spaces. I'd rather avoid, or even supersymmetric spaces. I mean, there is a certain freedom here. But we will be in a better position to discuss that once we have this guy under control.
What's the motivation for this big excursion? I mean, you already know how to calculate everything with Gaussian ensembles of random matrices.
There were lots of big excursions.
Well, if we want to calculate correlation functions of a Gaussian ensemble of random matrices, we can just do it.
Yes.
So what's the motivation for going through perturbation theory, non-single model?
So I'm using, how do you classical mechanics? You do harmonic oscillator in 10 different forms, right? And that's precisely what we are doing here. We are working in a random matrix setting because I can sell you and introduce to you all these concepts in a way which is not made complicated by, I don't know, Fermi surfaces and all that stuff. So all these concepts I'm introducing here have an absolutely straightforward generalization to more complicated settings. It's just a nutshell environment in which we, of course, we would not do that to open matrix theory. Yeah, it was a...
Yes, can you simply repeat what's the interpretation of the flavor space and the color space? How does it connect to the unitary time evolution?
Mm-hmm. If you have some kind of time evolution, say unitary or something or whatever, you fix the space here.
Why the flavor space? Why does evolutions in the flavor space?
No, that is it. I mean, to begin with, we are sitting here in this color space.
Okay, yes, that's right.
And then we go to project to low energy excitations.
And average.
And average. And we get some kind of field theory with its own, if you will, dynamics or structure. And that structure is no longer in this kind of time evolution space because we have traced out all degrees of freedom here, in a way, averaged over them. But the complexity or the physics now sits in this partner space, acting on the flavor and try to argue how it happens. You get these diagrammatic structures where all
it's not clear for me from the beginning. Where do you have the color and the flavor space?
Initially, suppose you...
Where does the flavor pop out?
Yeah, good. Suppose you compute the correlation function, G plus, G minus, G plus, G minus, and you have 10 of them. So then each of them corresponds to one of these closed lines or non-interrupted lines, right? And we have to label them. So we give them a label. And this label introduces a new index structure. And this index structure, which we introduce in this way, say that would be A1, A2, A1 plus, A2 plus, A1 minus, is this bookkeeping index which we introduced.
What do you mean? Sorry, I don't understand. What do you mean by label? What do I have an advanced and a Carly Green's function. What do I label? What's the degree of
you give the lines. I mean, on the level of diagrams, you give the lines a number. Each line carries a number. Line number 1, line number 2, line number 3. You have to do this counting. What we will do tomorrow is we generate this green function in terms of generating functions.
So okay, sorry, I still don't understand. When you do normal diagrammatics, you don't put some artificial labels on the lines.
You're calculating a 10th order correlation function. You got to put some labels on.
Yeah, you have to put some labels.
You're not used to doing 10th order correlation functions, are you?
Yeah.
Well, I'm not.
Yeah, me neither.
No, suppose you want to compute.
But that's what he's doing. He's doing a correlation function of very high order, which we're just not used to.
Say you want to compute a conductance correlation function in diagrammatics and so on. So you start drawing lines, 4 of them in this case, to retard to advance. So you somehow have to discriminate.
So wait, that's like an external indices or?
No, they're just say suppose we want to compute the conductance of a metal. Or this would be the second moment of the conductance. So then we need one retarded and one advanced here. This is called current correlation function of the x prime. And now we have another one, y to y prime, and here we have another. So somehow, if you look at this, you have to put a sticker on them. Which line are you talking about? Because now draw a complicated spaghetti. Yeah. And you have to tell, you look somewhere in your tens loop out here, and you have to tell me which of the 4 lines is doing what. Or that we need later.
So Alex, isn't like, simpler context that maybe everybody, people are maybe more familiar with. Say you study just perturbability of OM model, and your fields have labels on it just because it's an air component field.
No, these are my original labels. I mean the color labels.
Well, so then you write down the diagrammatics, and so you trace the line. You trace the indices of the lines in your Feynman diagrams. That's what these are, right? You no longer have any. You summed over all the time and space, and now you're just tracing your indices of your field through your Feynman diagram. Is that what you mean by flavor?
No, that's the color.
Yeah. I need to write one line, and this will become clear, I think, I hope. And that we can understand, I think, what is meant. And if I don't do it, Alex will do it for me. But yeah.
So just one more. Does the dimension of my flavor space depend on what order of perturbation theory I'm doing?
Yeah,
no. What order correlation?
What order correlation function
you calculate.
Okay.
And then if I can throw, maybe it's helpful to some of you, if you work with replicas or Keldysh or supersymmetry or whatever, you need additional counting labels to just, and all that